Have you ever wondered what our sun looked like when it was a very young star? The James Webb Space Telescope, JWST, has made a stunning discovery about our star, offering a unique perspective on its early stages. For the first time, we can observe the sun in an entirely new light. The JWST's most recent observation provides fascinating insights into the early life of stars and the massive processes that could have shaped our sun in its youth. Have we just unlocked another of the universe's great mysteries, thanks to this groundbreaking telescope? What other secrets still await us in the cosmos? The James Webb Space Telescope is a remarkable representation of how far technology has advanced. Since its launch, our ability to study the universe has grown exponentially. Through its latest mission, the JWST has demonstrated its incredible ability to probe the deepest mysteries of space. It has shown unparalleled technical superiority, especially when it imaged the object HH21, a Herbig-Haro HH object, an incredibly young star that, while still in its early stages, is already launching powerful jets into space and starting to form its environment. The JWST's observations of HH21 have provided a wealth of information about the energetic phase of star formation and, by extension, the early stages of our own sun's development. These observations are crucial for understanding the processes that occur during the formative years of stars. Herbig-Haro objects, first discovered in the 1950s by astronomers George Herbig and Guillermo Haro, are one of the most fascinating astrophysical phenomena in the regions of active star formation. These objects consist of narrow jets of gas expelled from newly formed stars and propelled into the surrounding interstellar medium at high velocities. As these jets collide with surrounding gas and dust, they create dramatic bursts of energy. Before the JWST, scientists had never observed the full extent of these high-energy jets, and it was difficult to imagine the violent forces at play in a stellar nursery. Young stars, far from being gentle, are incredibly powerful. The forces involved in star formation are immense, and even in the first billion years of a star's life, things are far from calm. It takes millions of years for a star to settle into a steady and stable state like our sun HH21, located in the Perseus constellation about 1,000 light-years from Earth, is particularly interesting because it is one of the closest and youngest examples of such objects. This makes it an ideal subject for studying the physical processes involved in the early stages of stellar evolution. The JWST has captured detailed images of HH21, revealing fascinating new details that were previously impossible to see. For the first time, scientists may have observed a binary star system forming at the center of HH21. The images show two bright, high-energy jets emanating from a central object. These jets contain particles like carbon monoxide and silicon monoxide, which are signs of intense processes taking place within the star and its immediate surroundings. The discovery of molecular hydrogen in these jets was a significant surprise, as it provides a completely new view of the chemical makeup and thermodynamic conditions during the early stages of star formation. The gradual accretion disk around the young star also suggests that other objects, such as planets and moons, could be forming. However, the intense outflows from the jets may make it more challenging for stable bodies to form. Despite this, JWST's study also showed that the jets of HH21 are slower than those in many other Herbig-Haro objects. This slower velocity could indicate that the star is in the early stages of its development, or that the processes in this star system are generally less chaotic compared to other stellar nurseries. The ability to observe such critical cosmic events up close with such precision marks a significant breakthrough in cosmology and promises to lead to even more exciting discoveries in the future. Observing the birth of stars also provides insights into how ionized gases and plasma interact. The energetic jets from young stars create shock fronts that act as visual boundaries for these young star systems. These early outflows are similar to the protective shell of our sun's heliosphere. The JWST is equipped with a range of innovative scientific instruments, including the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, the Mid-Infrared Instrument, MIRI, and the Fine Guidance Sensor, FGS. These instruments allow astronomers to detect even the faintest light from distant young objects that would otherwise be invisible to our eyes. By utilizing infrared technology, the JWST can see through dust clouds to uncover hidden regions of the universe, providing direct insights into the development of young stars and their environments, often obscured by thick layers of dust. Thanks to the JWST's high sensitivity, astronomers are now able to study distant star-forming regions with unprecedented detail. Not only can it capture these faint light signals, but it can also analyze them, allowing scientists to gather information on the jet's composition, temperature, and the chemical elements involved. Herbig-Haro objects like HH21, which are part of dynamic star-forming regions like the Orion Nebula and the Perseus Cluster, are ideal for studying the chemical cycles in space. These regions are rich in gas and dust, creating the perfect environment for star formation. Stars form from the accumulation of matter influenced by immense forces, and the jets ejected by young stars travel through space at incredible speeds, sometimes reaching several hundred kilometers per second. Since its introduction, the universe has undergone many changes, beginning in a dust storm and gas cloud that marked the starting points of planetary formation. The process of planet formation is not fixed, but the gravitational forces and conditions surrounding each planet shaped its development, from gas giants like Jupiter to rocky planets like Earth, and even smaller bodies like Mercury or Pluto. These celestial bodies all played a role in the early stages of our solar system's evolution. The study of the cosmos has been revolutionized by advanced telescopes, like the James Webb Space Telescope, JWST, which offers unprecedented views into the deepest corners of space, unveiling phenomena that were previously invisible or poorly understood. Thanks to its cutting-edge technology and capabilities, the JWST marks a significant leap in our ability to explore and comprehend the universe. One of the most fascinating aspects of the JWST's observations is its ability to peer into regions where stars are in their infancy. These stellar nurseries, scattered across galaxies, serve as cosmic laboratories where star formation unfolds. Understanding this process is crucial, as stars are not only luminous objects but the building blocks of galaxies and the source of the elements that make up planets and life itself. The JWST's instruments, such as the Near-Infrared Camera (NIR-CAM) and the Near-Infrared Spectrograph (NIR-SPEC), are specifically designed to detect faint infrared signals emitted by young stars and their surrounding environments. Infrared radiation is particularly valuable for studying these regions because it can penetrate the dense dust clouds and gas that obscure star-forming areas, revealing hidden processes. One of the key phenomena observed by the JWST is the gradual accumulation of material onto young stars. As a star forms, its gravity pulls in surrounding gas and dust, creating a rotating disk known as an accretion disk. This stage is vital for stellar development as it provides the raw materials from which planets eventually form. By examining the chemical composition and dynamics of these disks, the JWST offers clues about how planetary systems like our own may have originated billions of years ago. In addition to studying individual stars and their accretion disks, the JWST also explores the broader environments of star-forming regions. These areas are rich in molecular gases such as hydrogen, carbon monoxide, and water vapor, which are the essential ingredients for star formation. By mapping the distribution and abundance of these molecules, astronomers can reconstruct the intricate processes that govern the birth of stars and the development of planetary systems. The JWST's observations have also provided new insights into the role of magnetic fields in star formation. Magnetic fields play a crucial role in shaping the dynamics of accretion disks and regulating the outflow of material from young stars. Understanding how these magnetic fields interact with the surrounding environment is vital for creating comprehensive models of stellar formation and evolution. One of the most awe-inspiring features observed by the JWST is the outflow of material from young stars in the form of jets. These jets, which can extend for thousands of light-years into space, are driven by intense magnetic fields and gravitational forces near the star's poles. Studying these jets allows astronomers to investigate the internal workings of young stars and gain insight into how they release energy and momentum into their surroundings. Another area of research for the JWST focuses on protoplanetary disks, the birthplaces of planets. These disks consist of gas and dust particles that clump together over time to form larger bodies, eventually leading to the formation of planets. By analyzing the composition and structure of these disks, the JWST provides valuable insights into the conditions under which planets form and the factors that influence their evolution. In addition to studying nearby stars and planetary systems, the JWST is capable of observing distant galaxies and quasars. By examining the light emitted by these distant objects, astronomers can trace the history of star formation and galaxy development throughout the universe. This research helps answer fundamental questions about the origins of galaxies, the distribution of dark matter, and the evolution of the cosmos itself. One of the remarkable capabilities of the JWST is its ability to perform spectroscopic analysis of distant objects. Spectroscopy allows scientists to study the chemical composition, temperature, and density of celestial objects by examining the wavelengths of light they emit or absorb. This technique has revolutionized our understanding of the universe, revealing the presence of complex molecules, heavy elements, and dynamic processes that shape both large and small-scale structures in space. While the JWST's primary focus is on distant objects, it also provides valuable data about our own solar system. By observing asteroids, comets, and other bodies, the JWST helps scientists understand the origins of these objects and their potential role in the history of Earth and other planets. Beyond its scientific discoveries, the JWST is a testament to human ingenuity and international collaboration. The telescope is the result of decades of planning, engineering, and cooperation among NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Its successful launch and ongoing operations highlight the power of collaboration and the dedication of thousands of scientists, engineers, and technicians around the world. Looking ahead, the JWST promises to unlock even more secrets of the universe. Its unparalleled sensitivity and resolution will enable astronomers to study the faintest and most distant objects in unprecedented detail. By observing galaxies at the edge of the observable universe, the JWST will shed light on the early stages of cosmic evolution and the conditions that led to the formation of galaxies, stars, and planets. Additionally, the JWST's findings will provide crucial data for future space missions and ground-based observatories, guiding further efforts to understand the origins of life, the formation of planetary systems, and the evolution of galaxies over cosmic time. In conclusion, the James Webb Space Telescope represents a major milestone in humanity's quest to understand the universe. Its advanced technology and scientific capabilities enable groundbreaking discoveries in fields ranging from star formation and planetary systems to cosmic evolution and the origins of the universe. As the telescope continues to operate and deliver new insights, it inspires future generations of scientists and engineers to push the boundaries of knowledge and explore the wonders of the cosmos. The speeds of jets, measured in kilometers per second, are key elements of the dynamic processes during star formation. As these jets interact with the surrounding medium, they heat it up and create stunning, curved features that are visible through our telescopes. Within this remarkable display, powerful physical forces are at work, along with a light show that highlights the components of the system, including electric and magnetic forces. These captivating observations reveal how jets interact with the surrounding material, helping to shape the cloud from which the star forms. Each light emission and every color observed by the James Webb Space Telescope, JWST, provides crucial clues about these processes. Watching these events unfold in real time, especially in their early stages, is like witnessing the birth of a star. Understanding how matter is incorporated into the cosmic cycle and how the final mass of a star is determined by the interactions of elements and gases enables scientists to make significant inferences about the forces at play. This, in turn, helps us understand the broader processes of matter formation in the universe. Although star formation is one of the most powerful energy processes known, it's difficult to grasp the idea that a young star can produce winds that extend hundreds of light years and push material into space. The jets from Herbig-Haro objects could be the remnants of the powerful angular momentum that causes dust disks to start rotating and condensing at the center. It's also possible that young stars use jets to expel the forces they no longer need, while simultaneously driving formative processes in the gas and dust clouds surrounding them. So far, jets have mostly been observed in young, forming stars, but we also know of very old galaxies that produce strong jets at their active centers. Some of these cosmic winds extend far beyond their galaxies. These winds likely disperse large amounts of material, which influences both the mass and the environment of the star-forming regions. The expelled material and energy play a key role in triggering new star births and other cosmic processes. We must also consider the role of magnetic fields around young stars. Magnetic fields are crucial for controlling the accretion process, where the star gathers gas and dust from the surrounding nebula. These fields also guide the direction of the jets. Magnetic forces are not only significant in the immediate vicinity of young stars but are present throughout the universe. These invisible forces direct charged particles and shape the evolution of entire star systems. In our own solar system, the magnetic forces mediated by the Sun's magnetic field are vital for maintaining the heliosphere, the protective bubble around the solar system that shields it from harmful cosmic rays. The Sun itself generates a complex and variable magnetic field that governs the structure of our solar system, affecting planetary climates, space weather patterns, sunspots, solar flares, and coronal mass ejections. These events sometimes have major effects on satellite operations, communication systems on Earth, and can even produce auroras. The study of magnetic fields in young stellar systems, such as the HH21 region, is an exciting field of research and is still in its early stages. By understanding the development of stars in distant regions, we can gain insights into the history of our own Sunday. Our star, at 4.5 billion years old, has undergone many of the same processes seen in younger stars, providing a glimpse into the forces that have shaped our solar system over time.